Okay, this is a video about symmetry and periodicity. This is part of the trigonometry section, and really it's about identifying multiple solutions to trigonometrical equations. So let's just have a look at this sine curve, for instance. So this red line is the sine curve. These axes, we've got theta going horizontally, and let's call it y going vertically. So the value of sine theta is mapped out by this red line. Now, you may well be familiar, if you like, with the least part of this, as sine of 0 is 0. And as we travel up to pi by 2, so all these are in radians on this diagram, pi by 2, 19 degrees in old money. When we get to a value of 1, and then for obtuse angles, it starts to reduce until we get to sine of pi, which is 0, then goes negative back up again to 0. So sine 2 pi equals 0. So this is the one cycle of the sine curve between 0 and 2 pi. So, but it may be new to you that actually the sine curve exists, for values less than or greater than those limits there. We may well be interested in, in some problems we may be interested in, maybe a wheel rotating or something like that. And if it goes around 3 times, it's actually rotated through 6 pi. And equally, if it goes backwards, it might have rotated through -4 pi or something like that. So we are genuinely interested in those, those ranges as well. So really, these go on to plus or minus infinity either way. Okay, so so a little bit more about that and what we sort of mean by the sine of pi as we sort of measure obtuse angles and so on. But let's imagine for a moment we're solving this equation, sine theta equals 0.5. Well, you probably should be familiar actually with sort of one of those standard angles, isn't it? Sine of 30, which is pi by 6. Is 0.5, so that would be a solution to this equation. And in actual fact, if it's actually shown here, the intersection between the curve and this line here, which is y equals 0.5. So there we've got that solution there. But actually, the solutions to this equation are all the intersections of y equals 0.5, this blue line, with y equals sine theta, the red line. And as we can see, well, we've got lots of them. There and there, but also there and there and there, and then going backwards, we've got that one and that one. So these are all solutions, and they all have values of theta associated with them. Okay, so how do we go about finding them all? Well, first of all, we can find the other sort of main candidates, if you like, using the symmetry. If you imagine the symmetry of this curve around this line, which is theta equals pi over 2, then we can see that this distance here, that little segment, if you can see that, is the same as that. So if we call this the primary solution, it's a bit arbitrary as to what the primary solution is. But for instance, if you were to think about acute angles, or if you were to look, use your calculator, then you'd probably get this solution here by pi by 6. Okay, so and then if we call this one the secondary solution, so it's the closest one to it in this case, but not always. And we can just use this little equation here. Is that so if this is pi by 6, this whole stretch is pi, and so we're sort of pi by 6 short of pi, which is 5 pi by 6. So those are our two solutions. So let's call that the primary and the secondary, and those are connected by this little equation. The secondary solution is equal to pi minus the primary solution. Okay. Now, what you might say happens if it turns out that we're actually looking at not that equation, but let's say this is y equals minus 0.5, this yellow line here. Now, in which case, we will probably, depending on the process that we use, we may well find this solution here. Right, okay, so, and in this case here, this distance here is going to be pi by 6, so this is minus pi by 6. The solution to this to y equal sine theta equals minus 0.5. But we've still got symmetry about this green line, haven't we? So this solution we're going to expect to be pi by 6 more than pi. So in actual fact, this equation still applies because we've got pi minus pi by 6. So minus plus, so that would be 7 pi by 6 more than pi. Okay, so we've got a way, therefore, of identifying from a solution another solution, and that's due to the symmetry. But we also must remember that these two solutions will repeat every 2 pi or 360 degrees in both directions. So if we get those two solutions and we add 2 pi to each of them, we've got another pair of solutions, and then if we add 4 pi to them, we get another pair of solutions. If we subtract 2 pi from them, we get another pair of solutions, and they're all valid solutions to that particular equation. The only thing will be is normally when we're facing these problems, we'll be given a range, so we're not being asked to present an infinite number of solutions. We'll ask generally to give the solutions between 0 and 2 pi, or minus 360 to plus 360, or whatever. Okay, now we've got a very similar thing going on with the cosine curve, and so we're looking at solving this equation, certainly with a blue line. And here we would have, well, it's cos pi by 3 is equal to 0.5. Or cos 60 in old money. Now, in this case, the line of symmetry they're probably interested in actually goes through pi, through pi here. So yeah, what have we got? So this distance here is the same as that distance there. This distance here is the same as the distance between this solution we're trying to find and 2 pi. So basically we've got something very similar, haven't we? And in fact, our equation, given the primary solution, we're looking for the secondary solution, then it would be similar, but not quite the same. In this case, secondary solution equals 2 pi minus the primary solution. And again, if we're looking at the negative values, then this little equation still works. We're going to end up with well, in this case, they're both positive anyway, but if we were to find this solution, that would identify this solution here. Okay, so that is through the symmetry. We get two sort of closely associated solutions, and then we use the periodicity, adding 2 pi to each of those, 4 pi, 6 pi, so on, minus 2 pi, and so on, to give us the solutions in whichever sort of range that we need. So that basically is symmetry and periodicity applied to the sine curve and the cosine curve. We're also generally interested in the tangent curve as well, and that's what this is the tangent curve here. So this asymptotes to pi by 2 here, and then on the negative side it asymptotes to minus pi by 2. But these repeat every pi, or 180 degrees. So this one's not so much about symmetry, but more about periodicity. I mean, we may be well interested in a sort of negative solution here, and I suppose you could regard that as being a symmetry problem. But with these problems, we tend to just be kind of adding pi on or subtracting pi in order to actually identify the other solutions. So if we have an equation like tan x I've used here equals 1, and we're looking between 0 and 2 pi, then our primary solution would be pi by 4, 45 degrees in old money, and then they're going to repeat every pi. So if we have pi to this, we get 5 pi by 4, and then another is 9 pi by 4, and so on. And of course, if we chose to go backwards, then the negative direction would be getting minus 3 pi by 4, minus 7 pi by 4, and so on. Now, if we had a slightly different equation, which actually is sort of typical of the sort of thing that we might have to solve, and we're looking for the solutions to this equation, tan 2x minus pi by 3 equals 1. Then what we've got these same things here, aren't we? Pi by 4, 5 pi by 4, 9 pi by 4, and so on. But basically, it's just a linear equation that we have to solve, but we're solving it for all these different solutions. So in order to kind of solve this, we need to add pi by 3 to each side of the equation, but that means we want to add it for all of these different cases. So that gives us 2x equals, well, adding pi by 3 to this gives us 7 pi by 12, and then we've got 3 pi by 3 added to that, 19 pi by 12, and so on. All these solutions here originate from the ones above. And then this is 2x, so if we want x, we just have to divide by 2, and then it's going to give us 7 pi by 24, 19 pi by 24, and so on. Now I've got 55 pi by 24 here, but in fact, having got to this point, we realize this is actually outside the range that we're interested in. It's greater than 2 pi, so we can discard this. And very often we need to kind of just make sure we're, if we're dividing by 2, as we are in this case here, we'll make sure we've got enough solutions such that when we divide it down, we've got the ones we need. Okay, so that is the tangent. And normally in these sort of problems, we're mostly interested in sine, cosine, and tangent. Right, so let's have a look at this. This is something called a CAS model, and I mentioned that just give a little bit of sense to what we mean by the sine, for instance, of an obtuse angle. It's pretty obvious, really. I think we're looking at acute angles. This is a unit circle, okay, so the radius is 1, and if we're looking at the black lines at the moment, these black lines here, so if we're looking at an angle theta, which is sort of described by this, the point being on the circle here, then what we've got is this is the adjacent. Now this is positive. It's going, it's going in the rightward direction. This is the opposite, which is going in the upward direction. So these are both positive. Now in this model, the radius is always positive. So I can see quite easily that the sine of this angle here is going to be the opposite over the adjacent. Positive over a positive, it's going to be positive, as are all those 3 trig ratios in this quadrant. So this is the first quadrant. We've got the second quadrant here, the third and the fourth. So they're all positive. Well, what happens if we're actually interested in this angle here? Okay, the purple line. So it's just taking us round to the radius is kind of pointing up to the left here. Now, in this case, we regard the opposite as being this here, which is still positive here because it's still going upwards from the origin. But the adjacent is actually negative on this occasion because we're going leftwards. Okay, so if we're interested in the sign, then yeah, we've still got a positive over a positive. Okay, so the sine of this angle would be this. And of course, it's the equivalent. It's the same absolute length as this angle, which is 180 minus this angle. This angle is 180 minus this angle, I should say. Okay, which takes us back to the symmetry, of course. And it's positive. But if we look at the cosine, of course, that's going to be this over the hypotenuse. And that's going to be negative. And the tangent, in actual fact, is going to be that over that. The opposite over the adjacent, which is also going to be negative as well. Okay, so just continues a bit further. We look at the green here, and that takes us around to this angle. And in this case, we're considering the opposite to be that and the adjacent to be that. Well, the opposite now has become negative. So again, the hypotenuse is still positive. So we're going to find that the sine is going to be negative over positive, so be negative, and the cosine is going to be negative over positive as well. The tangent is going to be negative over negative, so that's positive. Right, so I think hopefully that will give you a little bit of idea of what we mean by the sine, cosine, and tangent of obtuse and reflex angles. Now, in this model, of course, we've noticed that in this quadrant here, all the three are positive. In this one, only the sine is positive, the other two being negative. In this one, only the tangent. And if you wanted to work it through for yourselves, you'd find that this is, it's in this quadrant, it's only the cosine that is positive. And we can relate that back to our curves. So again, you might want to just flick back and just verify that that is the case. Right, okay. So that is that. Now, another thing that isn't really to do with periodicity or symmetry is this called Pythagoras model, but it's something that crops up in these types of problems, so it is actually quite useful. And that is just to say that if we're told that sine theta equals 3/7, then if we draw ourselves this little right triangle here with the opposite 3 and the hypotenuse is 7, we can calculate the length of the other side as being root 40, and therefore that gives us an easy way of actually saying what the cosine of theta is, root 40 over 3, and tangent 3 over root 40. So it does crop up in these kind of problems. Right, okay, so now I'm just going to do one example. There'll be further worked examples on these for you to root out, see it on various videos, but let's have a look at this. Find the two solutions of the equation sine x equals sine of root 41 for 0 to 360. So this is an angle here. In degrees. Doesn't have a degrees mark, but since the range is given in degrees, then we're safe to assume that that is in degrees. So square root of 41 degrees, which of course is something like about 6 1/4 or something like that. Yeah, so fairly small. Give your answers in exact form. So probably surds involved there somewhere. Okay, so right, we're drawing a sine curve here. And so as with these things, we're looking for the intersection between the value, this value line here, and the curve. We don't know what the value is, and we don't need to know what it is in actual fact, not for this particular question. Now, one of the solutions to this is staring us in the face, isn't it? It's x equals square root of 41, so that's pretty straightforward. So if we will look at this, then we're actually saying there is a solution here. So regardless of what this line is, we don't need to calculate it. We could do, but we don't need to. This value along the x-axis, that is the square root of 41 degrees. Now, we know from our symmetry, of course, the symmetry line here, that our other solution, or the next solution, let's say the secondary solution, is 180 minus root 41. That's the little equation right at the top of the presentation, the video. So there we go. So this is another solution, 180 minus 41. Now, we've got both of these repeated every 360. So we've got another solution here, which is 360 plus root 41. But it's outside the range that we're interested in. So that's why I've shown it in grey. So basically, these are our two solutions to this equation. X equals square root of 41 and 180 minus square root of 41 degrees. Okay. I've kind of shown the CAS model here. It's not really needed for this, but I think it just kind of helps to illustrate that, you know, as the angle increases around here, this opposite is now getting smaller and smaller and smaller, which reflects the fact that the line is going down here. Okay, so that I think is as much as I want to do at the moment. And as I said, there'll be worked examples to supporting this that you can try and root out. Thanks for listening.